Good morning, everyone. We are Group 5, and today we will be presenting our analysis of algorithm for smart campus navigation as part of our algorithm design and analysis group project. Our goal is to identify and evaluate the most effective shortest path algorithms to help students and visitors navigate the campus efficiently, even when real-time obstacles like construction zones are present. This presentation combines theoretical algorithm analysis with real-world applicability within a university setting. Navigating a modern campus environment is more complex than ever. Users need fast and accurate directions that consider accessibility, life obstacles, and multiple routing options. Our goal is to analyze and compare three algorithms, which is Dijkstra, A*, and Floyd-Warshall, to find the most suitable one for smart campus navigation. To do this, we combine theory from textbooks and research with a real-world simulations of a university campus. We focus not only on speed and memory usage, but also on how each algorithm handles the needs of a smart, accessible, and responsive navigation system. We selected three algorithms based on their strengths in solving weighted graph-based pathfinding problems. Dijkstra's algorithm was chosen for its accuracy and reliability in finding shortest path with non-negative weights. A** algorithm adds efficiency by using a heuristic to guide the search, making it ideal for real-time navigation. Floyd-Warshall algorithm computes all past shortest path and is useful in pre-computing routes for static environments like printed campus maps or server-side applications. We deliberately choose these three to represent a diverse set of strategies, which is single source, goal-driven, and all pairs to ensure a well-rounded evaluation. These decisions was made collaboratively within the group after reviewing multiple sources and debating the best fit for the case study.
Assalamualaikum. So I will explain the Dijkstra algorithm which made into one option for our smart campus navigation. So the Dijkstra algorithm is a classic short path algorithm used to calculate the minimum distance from starting point to all other nodes in the graph with non-negative edge. So in the context of the campus, each node represents the building or the key location, and edge represent walkable path or corridors. The algorithm ensures that students or staff can find the fastest route from any one location, such as their current location, to all other points of interest. This makes it especially useful for real-time navigation when the user may want to reroute or consider multiple destinations. The time complexity of the Dijkstra algorithm is big O of V plus E log V when a priority queue is used, which means the algorithm running time grows based on the number of nodes and edge multiplied by the logarithm of the number of nodes. The priority queue is like a smart waiting line that always let the closest or most important location go first. In the Dijkstra algorithm, this means always picking the node with the smallest current distance to explore next path. So the Dijkstra can quickly find the shortest path without checking every single option. This means the algorithm performs efficiently even as the number of locations and paths increase. Meanwhile, the space complexity is big O of V plus E. This represents the amount of memory the algorithm needs based on the total number of nodes and connections, which is acceptable for typical university campus environment. However, one trade-off to consider is that the algorithm is efficient with agency list and priority queue, but can become memory intensive if implemented using a full matrix, which is why we tailor our data structure accordingly.
Okay, so my name is AHMAD and HAKIMI, and about the A* algorithm. The A* algorithm is an effective and popular pathfinding method that merges the advantages of Dijkstra algorithm and greedy best first search to efficiently determine the shortest path. It is often used in GPS navigation systems, robotics, video game AI, and network routing because of its capability to make informed choices based on the true cost of reaching a node and an estimated heuristic of the remaining distance. So the A-star algorithm employs the equation which is Fn. Fn is the capability to make informed choices and equal to Gn plus Hn, which is the Gn represents the cost from the initial node and Hn denotes a heuristic approximation to the target. Regarding time complexity, A star can reach up to O in the bracket B the power of D, where B represents the branching factor while D denotes the depth of the path path. Particularly in the worst case scenario with a poor heuristic. For the space complexity is like wise O, B, D, since it retains still O, B, power of D, since it retains all visited and unvisited nodes, potentially using a significant amount of memory in extensive or intricate search areas. This results in a trade-off between time and space, so the A-star can provide quick and optimal outcomes with an effective heuristic, but it might demand considerably memory, rendering it less suitable for memory-limited settings. So variants such as IDA and memory-bounded A+ tackle these constraints by decreasing space consumption while incurring longer processing duration.
Application explanation. The Flash algorithm provides a comprehensive solution for determining shortest paths between all pair of nodes in a wave graph. This makes it especially suitable for campus navigation system where user may need to find optimal routes between any 2 points. The algorithm operates by internalizing a distance matrix with direct edge weight between locations, systematically improving this estimate by evaluating paths through each possible intermediate nodes. Guarantee optimal routes between all location pair after completion. The key advantage for campus navigation include simulation compilation of all possible routes, and ability to handle navigate edge ways, consistent performs regardless of query patterns, ideal for static environment where path data change infrequently. Time complexity analysis. The algorithm using OV3 time complexity stems from its 3 nested loops. Outer loop iterate through all possible intermediate nodes. Middle loop consider each node as a source V and then inner loops evaluate each nodes as a destination. Particle implication for 50 location, 125,000 operates. For 100 location, 1 million operation. Become impractical beyond 1,000 location. Deterministic performance ensure predictable runtime, lacks optimization available for single pair Q. Space complexity analysis. The algorithm maintains AVXV distance metric, resulting in OV2 space complexity. Service requirement 50 location, 2,500 entries. For 100 location, 10,000 entries. 500 location, 250,000 entries. Memory characteristic, quadratic root limit scalability, full metric required, deep side graph sparsity, enable path retrieval post completion, acceptable for moderate size campus network. Time space trade-off. The algorithm presents clear trade-off between computational resource and functional advantage. Complete all pair solution in single computation. Content time replicability after initial processing. Handle negative wave gracefully. For limitation, cubic time complexity limit graph size, quadratic space requirement not suitable for dynamic graph with frequent updates. Then optimal use case, static network with 100 node system requiring frequent all pair queries, environments where pre-processing is acceptable. Alternative compression, Digitstra better for single source queries, Johnson more efficient spare graph, A-star superior for dynamic environment.
Now that we have analyzed each algorithm individually, let's summarize our findings and present our final recommendation. First, from a performance perspective, Dijkstra algorithm has a time complexity of O, V plus E log V, and space complexity of O, V plus E, making it ideal for real-time single-source routing, such as when a user needs direction from one specific building to another. A-star algorithm is even faster in practice with O b to the power of d time and O b to the power of d space complexity, where b is the branching factor and d is the depth of the solutions. This makes it especially suitable for goal-directed navigation with a good heuristic, like finding the fastest way to a class from a dorm. Floyd-Warshall has O v to the power of 3 time and V square space complexity, which is more memory intensive, but it's excellent for pre-computing all past shortest path, such as in static, digital, kiosk or back-end system. In terms of decision making, we evaluated other algorithms like BFS and Bellman-Ford, but excluded them due to limitations like lack of weight support or inefficiency. After comparing complexity, use cases and trade-off, our final recommendation is use A-star for real-time navigation where a user inputs a start and destination. Use Floyd-Warshall for kiosk or bash queries where pre-computed routes improve speed. Keep Dijkstra as a robust fallback, especially if heuristic data for A-star is not available. Finally, in terms of group autonomy, we divided tasks based on individual strengths, which is research, writing, design, and algorithm coding. We set internal deadlines and review each other's work regularly. All decisions, including algorithm selection and presentation structures, were discussed collaboratively and supported by references and practical considerations.
So for the question and answer session, for the first question is why did our group choose over A-star over other informed search algorithms like best first search or greedy search? The second is what would be the main consideration if we were to implement this navigation system in real time using this algorithm? And the third question is if the university expand and the numbers of campus building triples, which algorithm would be scaled the best and why? So to answer the question from previous slide, that we choose A-star because it combines the strength of the Dijkstra algorithm and best first search, unlike the greedy search which only use heuristic and may miss the path or the best path. So the A-star guarantees the shorter path if the heuristic is accurate. This makes A-star more suitable for campus navigation, where both speed and accuracy are important. So for the second question is that the key factor to consider are speed and memory. For real-time use, A-star and the Dijkstra need to work quickly and without delay. A-star work well when the goal is known, but it needs a good heuristic and use more memory. So the system should be also handle change like construction by updating route in a real time using live data. And the last question to answer is the Dijkstra algorithm is more scalable when using an adjective or adjacency list with a min heap. A-star is also efficient for searches with a known destination and good heuristic. Floyd-Warshall is not suitable due to its high time and space cost. For large campus, the mix of the Dijkstra and A-star is better for performance and management. That's all from us. Thank you.